Guys, before we start, there are some things that I want to talk about. The first thing is I did wear my lenses yesterday and today, so I can't see your faces. So I can barely see Mr. Wallace's face right now, so I don't know who you guys are. So when you're asking me questions, please tell me your names as well. And the other thing is there anyone involved in Math Society? Today we had a chair election. It's for me. So today we're going to do firstly a group recap. We're going to recap what we learned last time, and we're going to talk about groups and abelian groups and their definitions, and then something called orders, permutations, and generators. Well, maybe not generators, but these two specifically. And then the other one is going to be Peg Solitaire, which is a type of a board game. Did anyone play this before? Does anyone know what Peg Solitaire is? No one? Okay, that's fine. And chess, which is something that you would be more familiar with. Does everyone know what a chessboard looks like? Yeah, perfect. And then after that, if we have time, we will extend onto the Rubik's Cube. So, do you remember what I talked about in the introduction of last session? Well, how I talked about no matter how I mix a Rubik's Cube, a 3x3x3 Rubik's Cube, there's an upper bound to the ways in which you can change it back to the shape where all the sides have the same color. So that number is going to be called God's number, which is, to a spoiler, is 20. It was actually 20. I checked it. My God.
So did I. It is 20.
It's 20?
Yeah, I checked it out.
Well,
sorry.
my friend says 19.
I think he was thinking of smaller or equal to.
Yeah. Yeah.
So, first, group recap. Can anyone tell me the 4 conditions of something called a group? So in essence, this was a set and a binary operator. Who remembers the 4 things? Let's go one by one. What is one of them? This table. E thing, yes. E thing. Do you mean this E thing or do you mean this E thing? Okay, this E thing. This is called the inverse. Then what is E? Can you tell me what E is?
What was the question?
Can you tell me what this E here is?
Zero.
It's the identity.
Sometimes.
Yeah, sometimes. And the identity is when you have the binary operator. Please be quiet a little bit. It's the identity operator where you have A, B equals EA equals A. So last time if we talked about just natural numbers and the addition, 0 would be the identity. Because if you add 0 to any number, it will just give itself. No phones, please. Can you tell me what the first one would be?
Oh, it's like you can flip it and it's still the same.
Yeah, that's. Oh no, that's actually a characteristic for abelian groups. And thank you for pointing that out. So abelian groups are just in essence all of these 4 and this together, right? So the first one we talked about last time was closure, where we have A and B from the set, and then if you apply the binary operator to both, this would also be in the set. And we talked about examples of natural numbers or rational numbers with multiplication. Can this table tell me what the final one was? Yeah, the bracket thing, correct. Yes, associativity, thank you. This bracket thing, which the official name for it is associativity. So we learned about the definitions of groups, but I didn't really tell you about why we care about these groups and why they're so significant in mathematics. So today we're going to generally talk about why these are significant. And last time the examples that we talked about are like natural numbers or integers or rational numbers. But the problem with these is that these are infinite groups. Like you have an infinite number of natural numbers. You have an infinite number of rational numbers. But on the other hand, there are also finite groups as well, where the set is composed of a finite number of elements, unlike rational numbers or natural numbers. So we'll give an example of this. Let's think about not this one. Do you guys remember what multiplication under modulo something was? It was basically multiplying it on applying modulo n, which is getting the remainder of that number. Correct? Yeah. So let's consider 1, 3, 5, 7 under multiplication by modulo 8. Here, one of the things that we can use is something called a Cayley diagram. So a Cayley diagram is when you put the elements and then you apply the binary operator to all of them. So 1, 3, 5, 7, 1, 3, 5, 7. So let's go in this order. Just shout out what each one of these are. One? Yes. This one?
3, 5, 7, 6.
Well, under modulo 8, so 1, right?
7.
Yes. And then I'll just fill out the rest, which would be 5,
3,
1. And if you see here, because this has to be a finite, because the number of elements in this set is finite, this also means that if you apply this binary operator to one of the elements continuously, it will have a cycle. So in here you can see a cycle that's 1, 3, 5, 7, 1, 3, 5, 7, 1, 3, 5, 7, and 1, 3, 5, 7. So one thing to note in a group that has a finite number of elements, unlike infinite ones where they can just go infinitely, in a finite set you would always have something called a cycle. And so here, if you apply 3 times 3 under modulo 8, this would be 1. And let's write this as 3 squared. 3 squared, 3 is congruent to 3 in modulo 8, but 3 squared would be congruent to 1 in modulo 8. 3 cubed would be 3. So here, in essence, you have a cycle that goes from 1 to 3, right? So in something like this, you can also see a cycle with 4 elements in there. And then we can write this as something called a permutation, where we're trying to write the cycle that happens within this group. Do you guys get what I'm saying? Yes. So to write these kinds of cycles down, we use something called a permutation notation. Let's say that 1 goes to 2, 2 goes to 4, 4 goes to 7, and 7 comes back to 1. Let's just say that there's some kind of group that if you apply the binary operator, this is going to happen. In this case, we write this as like this. So 1 goes to 2, 2 goes to 4, 4 goes to 7, and 7 goes to 1. You can also write this as, just for the sake of simplicity, we already know what's up there because 1, 2, 4, 7 are the elements in our set. So we just skip the upper part and write this as 2, 4, 7, 1. Here, we can write the cycle because 1 goes to 2, 1 goes to 2, 2 goes to 4, 4 goes to 7, and 7 again goes to 1. This is how we want to write a cycle in a finite set. And here, after we apply the same thing 4 times to number 2, this element here, which is 2, it would come back to itself. So we write this as, so to generalize this, let's say that there's an element A within the group X. And then if we apply a lot of the same binary operator with respect to A to the single A here, let's see that this comes back to give us A. This is what happens in a cycle, correct? Then we can write this as a to the power of G equals E. Or no, let's actually write this as a to the power of G equals A. And if you apply the A inverse to each side, this would be AG minus 1 equals E. And then here we see that the order of A equals G minus 1. Because it took G minus 1 times to come back to the identity element. This is what an order, in essence, of a group is. Are there any questions? Everything clear? Okay. And then from this fact that you got here, we can also call something as a generator. A generator is then you have one element, and then A squared. So let's say that A is an element in the set X, okay? And then the order of A is, let's say that is G. And then let's say that we have like this set of A to the power of some things here. This would be the total set of X, right? Because X was formed by this, and by closure, this should be X. So here we generated the group X using only A and applying the binary operator and A to itself. So here we will say that A is the generator of this group over here. Do you remember how last time we talked about how integers under addition is also a group? Do you all remember this? In here, if you add 1 to 1, this would be 2. And if you add 1 to 1 to 1, let's actually use natural numbers. If you add 1 3 times, this would be 3. So here in this group, 1 would be the generator of this group here. Is everyone following? So these are just basically how we will want to name these name these special elements of groups in order to communicate them a bit more effectively. You can solve some questions about these other characteristics like cycles or generators next time, but today let's talk a bit more about how these can be applied in areas like board games like Solitaire or chess. So since no one knows what Solitaire is, it's basically a board game. So this is the board for a game of Solitaire. You would have pegs here, all over the board, except this one point here. And then if we have in Solitaire, if we have two pegs here, we can do a movement. If one square here is empty, we can move this over here. So the peg would be here instead. But the one that we went over, we can just take it away. This is the rule in Solitaire, and there is only one rule. Very simple, right? So the aim of this game is to have only one peg left at the end. But if we have a peg left somewhere else than the center square here, we call the player an outstanding player. And if you have the peg left in here, and you erased and you removed all the other pegs, and you have only one peg in here, we call that player a genius. So the essential question is it possible to do that? Is it possible to be a genius, and is it possible to be an outstanding player? So if so, what are the possible places that the final peg can be on? That's the mathematical question that we can kind of take out from this game. Do you guys want some time to discuss among your groups and talk about this, or should I just go into a solution? Some time to talk? Yeah, then let's have like 5 minutes for you guys to discuss among your groups or just have individual thinking, and then let's talk more about it. Oh, I'll just spoil it now. Alright. So, is there anyone who found the answer to either one of these questions?
Chessboard.
Is it chessboard? It's kind of similar with the solution for a chessboard as well. Then is there anyone who became an outstanding player or a genius? Is there anyone who found a way to get only one peg left? Anyone? Okay.
Anyone do better than 2?
Yeah, it's totally fine. You don't have to be disappointed, because this actually took a very long time for real mathematicians to solve this. So the overall solution to this is we put a color or maybe like a variable to each one of these squares. So we're going to use X, Y, and Z because I have only 2 colors in this one. So let's name each of these squares X, Y, Z. But then on here, on the next one, I'll name these Y, Z, and X. And in each of these ones, I will call them CX, Y, CX. So what essentially you're doing is that you're naming each of the squares with these x, y's, and z's. And you'll soon see why I'm doing that. What's that? Yes, so we name each of these squares like this, and then remember that this is the only place where we don't have the peg. So with x, y, and z, the key to solving this problem is that you construct a group with x, y, and z. Let's say that, so let's have x, y, z. So I'll write this. The notation for this group, so of course the set would only include x, y, and z, but the notation would be, if I write x plus y equals z, I am writing that the peg on x, this is the one that is moving, moves over y to z. This would be our notation. So if we have x, y, z, and if I have a peg on here and here, if I write x plus y equals z, this would mean that I am moving the peg on x squared to z squared. So this would mean that both of these go away, and I would have the peg on z. This is going to be our notation. But the key thing to notice here is that, no, not. And because this is moving over 2, this wouldn't be a abelian group because x plus y plus z would be different from y plus x plus z. So to prove that this is a group with x, y, z and this binary operator here, this looks like an addition, but it's actually not because you defined it in a different way. This only looks like addition, so don't be confused by it. So if you do this, you'll get that all of the outcomes are something inside x, y, z, so we prove closure, and also for the sake of having an identity element, we'll just include 0. So x plus 0 would be x. So this would be just making the peg remain where it was. If we have x, y, z, and the peg is here, x plus 0 plus x plus 0 equals x would be just making this remain right here. So with this, we now know that this is a group, so what? So the really essential thing to note here is that we can also do operators, we can also compute things like x plus y plus z. And if you look at this, x plus y equals z, and z plus z would equal 0, right? So here, you can see that x plus y plus z this in essence equals the identity element. So if we take this back to here and implement it here, we know that this is the only square that's empty. So we can get the sum of the squares where the peg exists. So in the configuration that we started with, if we add up the things, these variables on these squares that we first begun with, it would be x plus y plus z, which equals 0. This also equals 0. This equals 0. This equals 0. And if you apply this all around, it would be minus y, because this is the only place that's empty, and the other ones are x plus y plus z, which equals 0. And note that minus y equals y. So with this, because the inverse of y equals itself in this group here, as we talked about how x plus x equals 0 and z plus z equals 0, and the same will apply for y as well. So in here, we get that the addition of all these squares that have the pegs in the configuration equals y. And then the other thing to note here is that if we do something like this, x plus y equals z, this doesn't change the total sum of the things that are on these squares. Do you get what I'm saying? So like in here, if it was x plus y plus z plus x plus y, even though I compute this and put it as z, the total sum will not change. So this means that no matter what kind of move that I do on this peg solitaire board here, the total sum of the squares that have a peg on it is going to never change. And we call it an invariant. So that's going to be an invariant, which means that it's never going to change no matter what I do on this board here. That means after doing a lot of moves to have only one peg remaining, the sum also needs to equal y. Do you get that? So in here, after we do that, so in order for us to finish this game and end up and become either a genius or outstanding player, we should have only one peg. And that peg should be on a square that says y. Because we said that the total sum of the configuration that we started with is y, and that should never change throughout the game. So at the end, we will either finish, so to answer this question here, it is possible to be a genius. Because because it's totally possible to end on this square here, because the sum of these squares do not change. And then all of these squares that say y, these are potential candidates in which we can finish our game. But the problem is that this is symmetric. So if we did some kind of move to finish in this square here, we should also be able to do the same thing here, right? Because let's say that's because if I was able to move this to here and get rid of both, I should be able to do the same thing in here. And this is just this same thing rotated by 90 degrees anti-clockwise. So by the same token, we should be able to do the same thing here, which means that if you're able to finish in this square here, this y here, we should also be able to finish in this z here. But that's a contradiction, right? Because we just said that the sum should equal y no matter which case. So that means that these cannot be possible. Because this board is symmetric, and if we were able to finish at this point here, we should also be able to finish at this point, but that's impossible. So it means that if we do the symmetry test, these are the points that are impossible to finish. Whereas if you're able to finish in this point here, yes, we can also do that in here, here, and here. So after passing the symmetry test, we get the results that only these 5 points are the points in which we can finish off this game. Does everyone understand? Are there any questions?
Can you explain why the symmetry is important again?
So if we finished here, we should also be able to finish here. Because if we did a set of moves in order to finish here, if we just rotate that clockwise 90 degrees, we should also be able to finish here. But then we proved that only the squares with y are the ones in which we can finish on. But then if we can finish here, it means that we can also finish here, which is a contradiction. So you aren't able to finish in the points that do not pass the symmetry test, and you're only left with these 5 points. So CC and that's 10 or 20? 20. Then let's basically extend this one here, and let's discuss about the European version of peg solitaire.
네, 만약에 y까지 도달할 수 있어.
Okay, so this is the European version of peg solitaire. The previous one was the American version. So in here, we have extra 4 squares that are attached to these 4 sides. And then just like the American version, you have the pegs on each of these squares except the center one here. And the rules are also the same. Then is it possible to be an outstanding player? Is it possible to be a genius? And if so, what are the possible places of ending this game? You can talk about this with your team. Okay, so because of time, did everyone solve it? Okay, then I'll just present the solution. And if you find peg Solitaire on the App Store or Google, you can also find like simulations or programs of this, so you can try more at home. So to prove the solution, we do the same thing that we just did, which is to basically name each of these squares x, y, z to all of here. And then to spoil it for you, if you add all of the squares in which you have the pegs together, this would give you zero, which is the identity element. But one thing that you can note here is that there's no square that's written 0 on it. And then also in here, because you're using the same number of rules, that's saying the same binary operator, the sum of the squares that you have the peg on would be an invariant, which means that it would also never change. So if you add it and you still get, so in the first configuration, you added all of them together and you got 0. But here, there's no square that says 0, which means that no matter how many number of moves that you do on the European peg Solitaire or how you do it, you'll never be able to end up with only one peg. But instead, what we can know from here is that you will be able to end with x, you'll be able to end with 2 pegs that are on x and y, or x and x, or y, or z, and we can also do a symmetry test. We can apply the same thing here, or maybe like x, y, z. So 3 pegs on x, y, z, which would probably be somewhere like here. Like this would be a possible configuration in a European peg Solitaire game. So these are, so in conclusion, it's impossible to have only one peg left in the European version, while it would be possible to have any type of configuration where the sum of the squares would be 0. So that's it. These are some interesting applications of group theory in board games. Next time, because we didn't have time to talk about chess and Rubik's Cube, next time I'll talk a bit more about Rubik's Cube and chess. And if there are any other topics that you guys want to talk about or learn, please email them to me or Mr. Robbins. Thank you. Good job.
Thank you, Sean.